Yes, thank you.
All right. So let me first introduce myself. My name is Brian Campbell, and I am with the NASA Wallops Flight Facility, and that's in Virginia in the United States. I actually live in the state of Maryland, which borders Virginia, but I am based at the NASA Wallops Flight Facility, and it's on basically the western portion of the Atlantic Ocean. So if you cross the ocean from where I live, you're going to hit Europe. So what I do there, I am a senior Earth Science outreach specialist. So I work on several NASA satellite missions. One's called ICESat-2, Ice Cloud and Land Elevation Satellite 2, and I'm going to teach a little bit about that today. And I also work with some other satellites like the GPM Global Precipitation Measurement Mission. I work with what's called ground validation. So we put instruments on the ground measuring precipitation, and then we can compare that to the satellite data. And then I've been working with another mission called SMAP. You might have heard of that, Soil Moisture Active Passive. It's a NASA/JAXA, Japanese Space Agency satellite that's in space right now looking at soil moisture. But today, I'm here to talk to you as the lead for the Trees Around the Globe student research campaign, which you may have heard of. And I'm also the tree science lead for the NASA Globe Observer and their citizen science tool. So today we're going to talk about tree height, because that's it's a part of the Globe Biometry Protocol, but it's also one of the 4 protocols on the NASA Globe Observer citizen science app. It's the newest one, and we've gotten over 25,000 observations from over 11,000 locations around the world. So we have lots of good observations coming in all the time from the NASA Globe Observer Trees tool. So let's get started a little bit about tree height and what that is, and then I'll take you into what the Trees Around the Globe student research campaign is, how you can become involved, what we're doing this year, and then I'm going to show you some of the satellites and instruments that are at NASA flying in space right now, looking at tree height from space. And then I'm going to take you into a website called Open Altimetry, where you can zoom into any part of the world and see if ICESat-2, the satellite, took tree height observations in any part of the world. So I'm actually going to zoom in. Maybe I'll zoom in somewhere, in Asia somewhere. I'm just going to do it randomly when I get to it. So you can take, maybe I'll zoom into India somewhere. And, since Desh is here and he contacted me I'll zoom in, into India somewhere, and we'll see if ICESat-2 took tree height measurements from there. And then I'll show you, based on this, how you can, if you have globe data, or if you have taken globe data with a globe observer, how you can then go and compare that data that you took with globe for tree height with what the satellites are showing. So hopefully I don't give you too much information, but I really, my goal here is to hopefully you will gain interest in what we're doing, and you'll all become part of the Trees Around the Globe student research campaign. So our campaign, here's our core team, and you may know many of these people. I'm here on the left. I'm the lead for the campaign. We have Dorian Janney. Dorian Janney is at the NASA Goddard Space Flight Center, and she's the cross campaigns lead for the campaign. Peter Nelson, who you may have seen before, he is the co-lead for the campaign, but he is the expert on the online tools and the data. So the data coming from Globe, the data coming from NASA, and lots of other places around the world. He's the expert in that. And then we have Dr. Christopher Schumann. He is what we call at NASA a subject matter expert. He is a cryospheric scientist and a glaciologist by trade, meaning he studies the Arctic and the Antarctic areas, and he looks at change over time, looking at satellite data. But he, on our campaign, is the subject matter expert, and he leads what's called Trees in the News. And a lot of you probably know Peter Falcon. I'm not sure if he's on this right now, but on this webinar, but he is the cross-country coordination lead, and he's at the NASA Jet Propulsion Laboratory in California, Pasadena, California. So this is our core team, and let's go a little bit further into the campaign. So I'm going to show you a quick, cool little video here, and forgive me if there's any lag, but that might be just your local connection, but the video isn't long. But this is a little bit about what the campaign is, so I'll let this run through. It's only just about a minute long. Actually, it's, yeah, about a minute. So hopefully that video gave a quick, it was kind of what we call a teaser into, what the campaign is about. The campaign is about looking at tree height in your own environment. And when you look in your own environment, you can figure out so many things. And we don't recommend that you only take tree height in your environment, but that's just what the campaign is focused on. What we want you to do is, when you're taking a tree height observation, take as many observations as you can in that same area at the same time. Because the more data you have in a particular area, the more you'll know about that environment. And then you can share that with the rest of the globe community and scientists around the world, and citizen scientists, other students, other researchers. So you can share that data and information with people from all over the world. And you see, we have, there's over 120 countries as part of the GLOBE program. Our campaign, we have 53 countries that are participating in the campaign right now. So we have a lot of people taking observations all the time. So, and what we want to do is focus on tree height, but then, since it's a student research campaign, we want you to be able to take data, collect data, or go through the GLOBE database, using the GLOBE visualization system, if you've ever seen that, or the advanced data access tool, to be able to take that data, find that tree height data and other data, and then develop student research projects. And we've started that going for you. We started that for you with the campaign, and I'll show you what I mean in a couple minutes. Basically, we've come up with a big question for you to, possibly answer by looking at and answering smaller questions. So it's a whole bunch of smaller questions that you can work your research on to answer this big question, which is the big, what's called the overarching thematic research question for the campaign. So,
can I see the screen? Okay, now it's okay.
Yeah, there was nothing that was just the end of the video. Yeah. So here we have what's called the year 3 scaffold structure. And I say year 3 because we're in the 3rd year of the campaign right now. It started September 1st, so it's pretty new for year 3. But what we're doing in the beginning from September, actually this should be through December, because we added it. September through December, we are focusing on the science of the campaign. So we're focusing on tree height, we're focusing on land cover, we're focusing on green up, green down, and we're focusing on the carbon cycle. We have a webinar coming up in the next November 11th, and it's going to be all about the carbon cycle. After that, after we focus on the science, we're going to go to the next phase here, and that's called the science and planning student research. So what we wanted to do is we wanted to give you the science first, and then in the next few months after that, we can focus that science on what the students and the ones who are participating in this webinar, what you can do with that science to help you go out and take measurements, and then develop some type of research project that you can submit to, like the GLOBE IVSS, or like a local science fair or science contest. After that planning, then when you submit to IVSS, we would love students to come back and present at the campaigns. Every year during the campaign webinars, we have students present their research. And it ranges everywhere from 5 minutes up to like 25 minutes, depending upon how extensive the research was. So in that 3rd phase here, you see March through May, we're going to focus on what was submitted, and if any students and teachers want to present the student research projects that they did and submitted to like the Globe International Virtual Student Symposium, the IVSS. And then at the end, we're going to have 3 months. We're going to reflect on the actual last 3 years of the campaign, focus on the research projects, and we're going to have a 1 to 2 day workshop where students, teachers, citizen scientists, researchers, anybody from Globe is welcome to attend that 1 to 2 day workshop. And that's going to be happening, June through sometime June, July, or August of 2021. So this is the structure of the campaign right now. And you can find all this on the website, and there's a link to the website later on that you can write down and check out later. But here's this question that I was talking about, the thematic overarching research question. The big question for the campaign is why are or why aren't there trees in my local environment? When you go outside, some places you see lots of trees. And then there's other places where you see hardly any trees or you see no trees at all. The question is, why is that? Why are there no trees in your environment, or why are there trees? And that is the big question that we want the students to answer during this year 3 of the campaign. And a way they can do that is to look at some smaller questions. And you can see here on the left, we have these smaller questions like, where are all the trees in your location? What is the tallest tree in your location? What type of trees are around me? What are the environmental conditions around me? And lots of other questions. So these smaller questions can help you answer this bigger thematic overarching research question of why are or why aren't there trees in my local environment? So that's what we're focusing on. Once you get the science of the campaign and you know how to do like the protocols and things like that for something like land cover and carbon cycle and the greenings, green up, green down, you can then try to answer or explore these smaller questions to help you in your research to answer this larger question. And please, once again, if you have any questions for me, put them in the chat, and after the presentation's over, we'll go through the chat together and I'll answer those questions the best I can. So a little bit about why tree height, because you might wonder, why does NASA and the GLOBE program care about tree height? Tree height is the most widely used indicator, so it's the most important thing of how well an ecosystem can grow trees, okay? You have to have the right amount of soil, the right amount of water, the right amount of sunlight in an ecosystem, and the right amount of actual organisms in that ecosystem to grow trees really well. And depending upon the species of the trees, of course, they're going to grow different heights. But the ones that flourish are the ones that grow tall, they grow full, they're the ones that have an ecosystem that is ideal for growing trees. Tree height allows you to track the growth of trees over time. So you can look, you can see, maybe 1 year the tree didn't grow that much because it was pretty dry. And then the next year there was a lot of rain, so you notice the tree grew pretty tall in that 1 year. So by looking at that tree height, you can look at what's happening in the ecosystem and you can track how the tree is growing over time. The GLOBE tree height observations really help researchers understand the gain or loss in what's called biomass. Basically, it's helping us understand how much carbon is pulled in from our atmosphere. Carbon is a pollutant in the atmosphere. Trees, through photosynthesis, pull in that carbon dioxide. They need it and they convert it to oxygen for us. So trees can either take in carbon dioxide from the atmosphere, they can release it also, but trees store a lot of carbon because the trunk of a tree, the branches of a tree, the leaves of a tree are all made of carbon. So that's all carbon storage. And the bigger the tree, the wider the tree, the more branches, the more leaves it has, the more carbon it's pulling out of the atmosphere and the more carbon it's storing. So that's super important because when you have a forest where there's lots and lots of really tall trees, that ecosystem is very, very healthy, okay? If you have an area, say like in the desert area, like in Los Angeles, California, you might have heard that there's a lot of smog in Los Angeles. Los Angeles is basically a desert climate. There's not a lot of trees compared to where I live in Maryland. So the air here in Maryland where I live is definitely healthier than that in most parts of Los Angeles because it's a desert environment, it's drier, not as many trees. The trees don't grow a lot. Most of them don't grow as tall and as full as trees in my area. So there's a difference in that ecosystem. We have, a biome in California that's like a desert biome. Here we have a biome. It's like a temperate biome where we have, a average temperature, like in the 70 degrees. It does get pretty cold here in the winter. But like Los Angeles, it doesn't get really cold there in that desert climate. It gets cool. It doesn't get super cold. Like they don't get like snow and a lot of frost and all that stuff that we get. A lot of ice. So we get a lot of that here. So, and I know many of your countries in like Southeast Asia regions probably don't get that as well. The snow and the frost and all that as much as we might over here. And one thing that's super important to my presentation today is that NASA missions utilize the onboard laser altimeter system. What that is it's basically a system that fires laser pulses, like a laser pointer. It's a big laser pointer in space that fires laser pulses towards the planet. They bounce off the Earth's surface and go back to the satellite again. Now, you don't have to worry about these lasers because it's not like the ones that you see specifically like on a laser pointer where you're not supposed to look at it. These satellites are so far away, these instruments are so far away in space, hundreds of miles away, that even though if it's really dark out, you may be able to see the laser, they pose no danger to anyone on Earth, okay? What they do is we calculate the time it takes the laser pulses to leave the satellite, bounce off the Earth's surface, and then come back to the satellite. And by doing that, we can tell how tall things are on the planet, like ice, like mountains, like how what the ocean height is, what the level of lakes are and streams and rivers, but then also trees and forests and wooded areas. We can see the height of them from space. So that's super important to NASA because we have those measurements from space, but tree height from the ground, like you would be doing with the trees around the Globe Student Research Campaign and the GLOBE program, you can look at the trees from below on the ground and then do comparisons between what you see on the ground and what the satellite sees from space. I show this graph here because this is about the Globe Observer, so the citizen science app. And what I mentioned earlier, when you're going out to take an observation, take as many observations as you can in one place at the same time. For instance, if you're using Globe trees and taking a tree height, go ahead and use the same app and take a land cover observation, and then look up and take a cloud observation, and then look around and see if there's any mosquitoes. And I know there's a lot of mosquito observations coming in from like the Philippines and Sri Lanka and Thailand and some from Japan. You're seeing a lot of mosquitoes there during parts of the year. So when you're out there, if you take observations of all four of these in one location, you're really helping GLOBE and other students and NASA really understand what's happening in your local environment. Now, we're focusing on trees for the campaign and some land cover, but we always want you to take as many observations as possible when you go out. We don't want you to have to take observations all the time. And remember, now we're in the middle of a pandemic. So if you go out and take these observations, you have to make sure you do it safely. Follow all your local guidelines and protocols. If your local government says don't go outside now, you're locked down, don't go outside and take observations. You can just look at it out your windows, and just say, hey, I can't wait till I can get out there and take some observations, okay? Please be safe, because that's the most important thing. Your safety comes first. It's the priority. And when you're allowed to and safely, take the observations, and be safe when you do it. Just wanted to let you know that's what we're looking for. We really want you to be safe first and then take the observations when you can safely. All right. So let me show you about what we've done with the campaign so far. This is the Trees Around the Globe Student Research Campaign. We started September 15, 2018. That is actually when the ICE-SAT-2 satellite launched into space to start its observations from space. But if you go all the way to the bottom here, you'll see that in this in the white flag here, we have, if you add the tree height, land cover, and green up, green down measurements from students and citizen scientists as part of the campaign, we have 55,782 actual individual measurements and observations coming in from over 23,000 global locations across the world. Okay, that's a lot of awesome data, but we always need more, because in order to understand our world, and our world's changing all the time, it's changing every second of the day, okay, we need observations all the time. I know we don't have observations from every second of the day, but we like to try to get as many as we can as possible, okay? So that's a lot of data for students to use for their research projects and for, you know, IVSS submissions. So if we look here at this map, this is a map showing you from just September 15th through September 15th, 2018 through today, October 29th. For you, it's tomorrow. It's actually October 30th. For me, it's still October 29th. We have about 30 minutes left in the day here until we hit October 30th, where I can join you in the second to last day in October. But we have participants from 52 countries. Actually, it should be 53. We just had one join today, and I forgot to change that. You know, we've had lots of webinars, and on the website, you can go back and look at the webinars that were presented, where there's professional presenters, there's student research presenters, all throughout the first 2 years and the beginning of this year so far. And we have lots of blogs. There's 37 blogs, actually, because I just did one today again. We have 37 blogs with almost 100,000 views. So there's lots of good stuff going on with the campaign. You can see the observations come from all over the world, and what you're seeing here is all the pictures you see are a combination of tree height and land cover pictures that were taken using the NASA Globe Observer Citizen Science tool. So the Citizen Science app, the land cover tool, and the trees tool. And just the little dots you see there, like the red, that's the mosquito habitats where those were taken. And then you have just the blue. The blue are just the trees. Sorry, that's green up, green down as well. The blue and the light blue and the dark blue, that's some green up, green down. And then we have some other things there as well. And the gray, there's some carbon cycle things in there as well. So there's lots of data there for you to use, all right? So a little bit about the webinar. The webinars that we have each month, we have them once a month, and we hope you can join sometime. They are, our major sections are Trees in the News, and that's with Dr. Christopher Schumann. And he focuses on a number of things. What is the most important things going on with trees around the world right now? And then also he looks at areas over time. He brings up satellite images of the same area, looking at the trees through time, you know, maybe 50 years, 100 years, just 10 years. If he sees a big change in a short amount of time, he'll look at that. So he will showcase how an area, a specific area, has changed over time. We have Dorian Janney, and she is focusing right now on what's called story mapping. It's how to tell your story of what's happening in your local environment visually. So she has, and if you go to the past webinars from last month, the one from last month, you can see what the story mapping is about. And she focuses this on, she started it with the GPM mission, the Global Precipitation Measurement Mission, and now she's starting to focus it on she did an example at the last webinar on the trees in her local environment and how to identify them, how to visualize and show a really cool way to map out a story to tell the story of the trees in your area. So, you know, that's going to happen every webinar. She's going to focus on that and build it each month. And then we have Peter Nelson. He is a researcher at the Oregon State University, but as I mentioned, he's the co-lead for the campaign. He's also the land cover science lead for the NASA Globe Observer Citizen Science app. But he is an expert in online tools and data analysis. And he talks a lot about things like, and I put an example here, NASA Worldview, which is a huge, amazing tool that lets you visualize so much NASA data you couldn't believe it. But it shows you on a map. You can create video time series. You can look at change over time. You can look at individual areas on a map, okay, of all this stuff, okay, all these awesome online tools. And Peter is the expert at that. And he showcases this at the end of each webinar for about 10 to 15 minutes. He focuses on a tool that you can use as a student and a teacher, especially as a student, to help in your data analysis of the data you've collected and in your research projects. So the protocols that we focus on the campaign, I mentioned these before: tree height, land cover, greenings, which are green up, green down. And green up, is in the springtime when the trees start growing and the buds start bursting and you get flowers and all that stuff. The leaves start coming out. Green down is in the wintertime, the fall and winter, when the leaves start falling, the colors start changing, okay, in a lot of these areas. And I know there's a lot of areas where, around the equator, you don't really see a lot of green up, green down, so it makes it a little tricky, okay. Stays presented. My cousin lives in Florida, just above the equator, so he has mostly palm trees and he doesn't see the change in leaf color that we get here. And then also the carbon cycle, which is a relatively new protocol. It's a little complicated. There's different ways to do it, but we wanted to show it because the carbon cycle is vital to all the other ones: the greenings, the land cover, and the tree height. And please also remember that we always like to say that trees are part of land cover. Okay, that's a thing, that's something we always like to stress. So when you're out taking these tree height observations, look around at the land cover and take an observation as well. So what we're doing at the campaign, we're really collaborating with other campaigns. We're collaborating really well with the European Phenology campaign because they focus on green up and green down and leaves and the carbon cycle. So what happens here is that if you'd happen to be part of the European Phenology campaign, when they're out taking a greenings measurement, we're asking that they take tree height measurements. So we have that comparison between those two. There's another campaign called the Urban Heat Island Effect Surface Temperature Field Campaign, run by Dr. Kevin Tchaikovsky out of the University of Toledo, and he is a Globe partner and member for as long as Globe has been around. But they look at land surface temperature. They use that temperature gun to measure basically the temperature of ground surfaces. So we want them to take tree height measurements when they're taking observations of surface temperature in urban areas, in anywhere, urban areas, neighborhoods, even rural areas, on grass areas, on areas where there's sidewalk and cement and like parking lots, all those places, and like in the shade of a tree and outside the shade of a tree. And then Globe Mission Mosquito, which a lot of you may be members of as well. There's lots of different things about mosquitoes that tie into what we're doing but there's something specific called a tree hole, where it's just like a knot in a tree where water can collect. And where water collects and it's a warm, arid climate, warm, moist climate, you can get mosquito habitats. And these tree holes can be potential mosquito habitats. And that's a good place for them to, if they find a tree with a tree hole, to find mosquito larvae. They can take a mosquito habitat observation and then also take a tree height observation. So this is how we collaborate with a lot of the Globe campaigns right now. So going into the last part of the talk tonight, I want to show you something about the NASA missions that are involved with our campaign, with the tree height measurements. So we have two here. One I mentioned earlier called ICESat-2. It's Ice, Cloud, and Land Elevation Satellite 2. And it fires off 10,000 laser pulses per second. And I have a video to show you that, which is really cool. So I won't talk a ton about that yet. But it fires off 10,000 laser pulses per second. And in every laser pulse, there's about 300 trillion photons. So basically, we're firing off these laser pulses. The photons are traveling to the Earth, and we're trying to get back as many of them to the satellite as we can. But as you probably know, if we're firing laser photons, lasers are light, right? Because lasers are light, they're going to scatter. They're going to get reflected. They're going to get refracted and absorbed by many different things, like the atmosphere, like different parts, like water in the ocean, like absorbed by trees and bouncing off at different angles. So we're not going to get them all back to the satellite. And I want you to think about, out of 300 trillion photons, how many of these photons do you think we actually get back to the satellite per 300 trillion? And there's a video here I'm going to show you soon that answers that. But I also wanted to mention this instrument on the right with the red laser beams. This is called JEDI, and it's an instrument that is on board the International Space Station, which I'm sure you've all heard of. The International Space Station is traveling around the Earth super fast right now with many instruments on it that are looking into space and also looking back down to Earth. JEDI is looking at Earth and firing off laser pulses as well, and it's measuring from the International Space Station, which is a lower elevation in space than ICESat-2, but it's focusing on tree canopy height. So it's looking at the entire height of forests across what's called the latitudes. It's between 51.6 degrees north and 51.6 degrees south. So it's getting those mid-latitudes, all the forests in the mid-latitudes, like the rainforests and areas like that. It's measuring the height of those forests around the world. ICESat-2 is traveling basically from North Pole to South Pole, and it's getting the entire planet. But once again, there's been parts on the planet so far that haven't been measured because the light never comes back to the satellite because it might be too cloudy, or it gets, all the light gets absorbed at some point, or gets scattered or reflected or refracted somewhere. So, but we do have over 7 trillion measurements from just ICESat-2 in 2 years, which is just an amazing amount of observations and data. Okay, that's a lot of data. I haven't looked at all that data. Nobody has time to look at all that data. That's why we have this tool that I'm going to show you in a second to visualize this data. All right, let me show you this video here. This is about ICESat-2. Since it's called ICESat-2, its major focus is on looking at ice, looking at the melting ice in Greenland and Antarctica and all around the world, and it has to do with how we look at melting ice and and focus on sea level rise. But what we're going to focus here is just what the mission is about, and you'll see why it's so important. So let me share this right now.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ICESat-2 adds the third dimension, the elevation. Repeating measurements from ICESat-2 will allow us to measure changes in the ice sheets or in the ocean or in land.
ICESat-2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat-2 is designed to measure those areas and will help us to understand what's going on with our planet.
So that was a little bit about ICESat-2, all right? And remember I asked you that question earlier about, how many photons out of 300 trillion do you think make it with each laser pulse? And here's the answer.
300 trillion. That's about how many photons in each laser pulse fired by the ATLAS instrument. It sounds like a lot, but as the photons sail through the atmosphere and bounce off the Earth, they reflect back, just like any light, in all directions. ATLAS receives only the photons that reflect straight back to the instrument, just about a dozen photons. That window of photons received must be very small in order to keep the timing error of those photons very small, which allows scientists to calculate elevation very precisely.
So basically what that said is that for every 300 trillion photons that are sent out, we get an average of about 300 trillion sent out, we get about 12 back. Only 12. Doesn't sound like a lot, right? But since we're firing 10,000 laser pulses per second, that means every second we're getting 120,000 data points or useful data every second from the satellite, and the satellite is on 24 hours a day. That's why we're able to reach 7 trillion observations, 7 trillion in 2 years. So that's a lot of data. And remember, it's not just trees, it's looking at the entire planet's height, things all over the planet. All right, so how do you go out and take tree height observations? And there's several ways with the GLOBE program you can do it. Here's a handheld clinometer, all right? This handheld clinometer is something you can find on the NASA website, on the GLOBE website. You can find it on the NASA GLOBE Observer page as well. And this one you just build, and it has to do with you just use straw, you use a drinking straw, a string, some tape, a scissors, pen or pencil, and then like something to hang, like a weight to hang off the string. And then you can go out and take tree height measurements using this. And there's instructions how to do that on the clinometer, and then also on the GLOBE website. That's one way. And then of course we have the citizen science tool, the NASA GLOBE Observer, where you can measure with your phone. So your phone has what's called a built-in magnetometer that can use you can use to measure angles. All right. Now, not all phones around the world have a magnetometer in them. So if you get an error that says it can't be measured, your phone just doesn't allow for it. The majority of phones do, but we found that in some countries that don't really work. We found some in China don't work, and there's some other ones in Europe that don't work. But this was just specific brands and where they're made, and I don't know all those brands. It's all because there's literally thousands and thousands of different brands of phones across the world. But you can use it if it has that built-in magnetometer, and you'll know if you try it out. But you'll be able to use it to measure the tree height, and it's super simple. So I'm going to show you quickly here just how easy it is to do. And I'm going to start this video, and I'm not going to run through everything, but this is all you need to do. To look at your local environment, you just look at your service conditions. I'm going to show you what to do when you look at the trees, okay? So these are my service conditions I'm putting on in the app. And then you measure the tree base. You hold the phone at eye level, where the camera's at eye level, and you align this dot to the base of the tree. And you click the screen. And if you like it, you hold the phone at the exact same spot, not moving it from your eye. And here I did it. I don't like it, so I'm going to do it again. And I'm going to get the top of the tree. And yes, I like that. And then you center the tree in the picture, and then press the screen again, and you get a photo. That's the one that'll show up on that map I showed you earlier. And then you walk to the base of the tree, counting your steps, okay? When you walk to the base of the tree, what you're doing is you're counting your steps. When you get there, you're gonna put in there how many steps it took to the tree. So what it's doing is it's using that math called trigonometry. So it's measuring the angle from your eye to the top of the tree. It's measuring the distance from the top of the tree in that angle to the bottom of the tree in that angle, and then it's measuring that distance to the base of the tree. And then if you have it set up, okay, you can use this map to align where exactly your tree is if you don't like what it says. And then you can also measure the circumference of the tree, okay? You can measure the circumference of the tree as well. And that helps us with that whole carbon information. So here's a link to our campaign website, and I have one more thing after this I want to show you. I want to show you that tool where you can go and look at the ISAT-2 data. But if you just go into Google and type in GLOBE trees around the globe campaign, it'll pop up, and we have some major sections here. A lot of the stuff that you saw today are on these pages, okay? And here's my email on the bottom. If you need to get a hold of me, ask me about the campaign at all, please do. It's brian.a.campbell@nasa.gov. Okay, but up here is the link to the campaign and all the campaign sections. Now, what I want to show you here in the last thing, in the remaining time before we go to questions, and I'll take only a couple minutes to do this, doing GLOBE and ISAT-2 tree height data comparisons. There's a lot on this graph here. I'm not going to show you everything, but this is a combination on the left side of what I'm going to show you with this image here. This is showing you what's called open altimetry. It's showing you ISAT-2 data. And on the bottom, on the left side, is showing you what I got from the NASA GLOBE Observer Trees tool and what I got from the NASA Land Cover tool on the app. And then I went over and I matched them up. ISAT2, you'll see in this box, see in the box over here, and then NASA Global Observer, and you can see they matched up really well. The canopy height, which is the tree height, 19.66 meters. For ISAT2, ISAT2 said it was 19.66 meters. Global Observer said it was 18.93 meters. That's very close. The elevation, 14.87 and 14.93. That was the elevation above sea level where I am, okay? And then the latitude and longitude matched up perfectly. So how do we do this? So have you ever wanted to look at satellite data like a researcher does? And this is where we're going to go. So I'm going to pop in to this tool. It's called Open Altimetry. And you should see it right now. And I'm going to click on Browse ISAT2 data. And this will take us to a map. It'll be a global map where you're going to see lots of green lines. Those are ISAT2 orbit tracks. So what we're going to do, we're just going to zoom into, let's go just zoom in to India, like I said I was going to do earlier. So we're just going to zoom. You can just double click. I should also mention what you can also do is, what you can do here on this little box here on the left, you can put in your longitude and latitude. So that's why it's important, because when you take a tree height observation with the app or with the clinometer and put it into the Globe database, you're going to get the latitude and longitude of the location of the tree you just measured. So when you get that observation, when you get that latitude and longitude, you can put it right in here at the bottom where it says center map on a point. You can put the longitude and latitude of that tree in there and make sure you see that longitude is first here and latitude second. And what happens is it'll center that area in the map, and you can zoom right in to see if ISAT2 hit that area. So we're going to zoom in, and you're going to see a lot of red lines pop up here. These are all ISAT2 tracks as well. So we're going to zoom in a little further here. Okay, let's just go. I'm just going to go randomly here. And I'm just going to click. Let's just use this green line. Let's just pick one of the red lines. You can use the green line or the red line. If you pick the red line, if you click on it, it'll tell you when ISAT2 was near that, where things were measured around that line. So let's just randomly click on, let's do the most recent one for this area, June 21st of 2020. So then what you see, you'll see this green line pop up. And you'll see these dots. These dots are the photons that I just told you about. These are the photons that made it out of the satellite, hit the Earth's surface, and made it back to the satellite. So then up here where it says select a region, up on the top left, I'm going to click on that. Then you'll be able to drag a little box around here. So I'm going to draw a box around just these photons, okay? Just going to drag around those photons. Okay, and then it'll say view elevation profile. So this is going to be where it's going to give you the height of things. So you're going to view the elevation profile. So check this out. Surface elevation means where it is above sea level, basically, okay, and the canopy surface, where it's sitting on the ground. But what we're excited about is what's down here called canopy height. That's also tree height. So if you happen to have measured a tree in this location at the same latitude and longitude, here you have this latitude, okay? You can then click on any one of these. I'm going to click on this one, and you can see it tells you how tall that tree was at that location. It happened to be 5.22 meters. So that's a pretty small tree. That's just over like 15 feet in the standard form, but 5.22 meters. But it looks like this looks like the tallest one in the area up here. Well, this is pretty tall. This is 22.39 meters tall. So this is a way that you can go in and take the tree height data that you got for the Trees Around the Globe Student Research Campaign observations, and the observations you took for the GLOBE program or from the NASA Global Observer Citizen Science tool, the TREES tool, and compare them to what ISAT2 saw. You can zoom right into your area. You can even put the latitude and longitude in of the tree that you took to see if ISAT2 hit there. Now, ISAT2 may not have hit your location, so you might have to look at another location because of things like I mentioned earlier, like all that reflection and refraction and all those absorption of the light, okay? So that ends what I wanted to talk about today. I wanted to show you this really cool tool at the end. I'm going to stop sharing my screen. I'm going to pop back onto it, and we can go through the chat if there's anything in the chat. I haven't been able to see the chat because I'm sharing my screen.
Thank you, Brian, for a wonderful presentation. I'm sure there are certain questions, and then I will hand over to Rod. Rod,
Yeah.
coordinate the questions. Rod, can you
Brian,
listen?
Yeah, Peter.
Hey Brian,
Yeah.
this is Peter. You got a lot of great questions in the chat. I can
Awesome.
just go over a few of them with you.
Go ahead.
Rod,
Sounds good.
Rod wanted. I was like, Rod wanted to know if everyone can view the ISAT and if there's a tracker available where they can go in and view where it's at.
Yeah, right now online there's not a specific tracker, but if you go and if you have an Android device, you can go into like the Google Play Store and type in ISAT2, and it'll tell you where ISAT2 is and where it will be, and even in relation to your area. Okay, but you can also go and check out the ISAT2 website because sometimes they put up there where the ISAT2 is located at the time. So, and that's just I'll put that link in the chat, the ISAT2 site that you can go on and check out. And yeah, you can check that out. But the app isn't available. The